Hi there, let's go over your guided questions for topic 6, which is about generators and motors, electric motors. Definitions: what's an electric generator? It's a device that converts moving or mechanical energy into electrical energy. So, the motion of machines. An electromagnet is a strong temporary magnet created by inserting hopefully an iron core into a coil of wire and then passing a current through the wire. AC, or alternating current, is electricity produced by a generator where the current flowing from the generator will change directions. And a dynamo, like one you would put on your bike to create light, maybe. A dynamo is a generator that produces direct current. Question 2, provide 3 examples of devices that convert mechanical energy into electrical. So most motors will do this. So let's look at your textbook for a minute for this. So a motor, like the ones in cars and stuff, will convert mechanical into electrical. So any device with an electric motor. Next, Hans Christian Ørsted wanted to show that there was no relationship between magnetism and electricity, but discovered just the opposite. What observations did he make? Well, this is really interesting. Ørsted took a battery and hooked up a wire, and then he took a compass and put it over top of the wire, and what he noticed when he turned the switch on to start the electricity, the compass needle deflected. Okay, so it went from north to depending. And so here's the picture of good old Ørsted when he was trying to do this. So there's Ørsted right there, and here's his little mini experiment, and basically what that did was, to his surprise, he discovered that current through a wire creates a magnetic field. And so then later Michael Faraday further explored this concept. So very interesting in that Hans Christian Ørsted didn't expect this to happen at all. In fact, he was trying to prove the opposite. Number 4 wants you to make a simple electromagnet and describe ways that we could make it stronger. So an electromagnet, we need a cell, so a battery, and then we take a wire and we coil it, a coil of wire. Then hook it up to the negative, and then inside we would stick a core, maybe like an iron nail. And when we turn the electricity on, this becomes a magnet. Not any magnet, an electromagnet. And it could pick up paper clips and stuff. So the question becomes, how do we make this electromagnet stronger? Well, number 1, We could make this a stronger battery, so make it, make it a 9 volt instead. How else? Number 2, we could increase the coils of the wire. The more coils of wire we make, the stronger. So more coils. And number 3, a third way we could make it stronger is all sorts of different cores work, but a small iron core is best. And so make your core iron. And so those are 3 ways to strengthen our electromagnet. And so let's just show you in the book. Here it is again. Here's our electromagnet. And Faraday basically discovered this. Next. Number 5. We have to go to the next page. Oops. Explain how electromagnets are used by maglev trains and MRIs. I think there's a diagram here. Let's go to maybe not. So, we talked about maglev trains before. Maglev trains, like the one in Shanghai, they have super conducting wires. So if you supercool a metal, you can create a magnetic field, and that's how the track works. Number 6, explain how a generator produces electric current, and then the difference between AC and DC current. So let's go to here. Let's go back to our picture of a generator. So here's a generator. Here are the components. So you need a magnetic field. So you have 2 permanent magnets, and there's a magnetic field going across there. Then you have a coiled wire. So it's kind of the opposite. Before, you had a coiled wire with a magnet moving in and out. This one's got 2 magnets, north and south, magnetic field lines, and you spin a coiled wire inside the magnetic field. And so when you do that, it generates electrical current, which can be hooked up to here. And the current alternates or flips back and forth. And if we graphed it, it would look like this. Here's a generator, so current goes in one direction. So here's our magnetic field. We spin this huge coiled wire, and that creates electricity. But as it spins, the electricity moves in alternating cycles. Sometimes they use a steering wheel analogy. So what happens is you put both hands on the wheel. You can keep turning without. Can you keep turning without letting go? No, you can't, because your hands must release. If you could not let go, you could only turn the wheel half a turn, then you're stuck. So the same problem occurs in a motor that's a generator. Let's do the next question. Label the parts to a St. Louis motor and give a brief explanation of how a St. Louis motor works. So here are the parts to a motor. There's a battery that's needed. These are called the commutators. This is the permanent magnet, and this is the armature. So here's how it works. When the battery starts up, the electrons move through here, and they move through the metal, and they create a electromagnet in the armature. So this is north and this is south. So watch this yellow dot. So what do we know? This is north and this is south. So these two push away. So this pushes away and spins downward. It's also pulled. So it's pushed and pulled because north and south attract each other. As it's spinning, so does this system here, the commutator. So now watch, it's spun, the commutator spinning, but then there's a gap in the electricity here. Okay, so there's a gap and the electrons stop flowing, but it keeps spinning a little bit. And eventually what happens is, see how this was once south? Once it spins, it switches and this becomes north in the armature. And once it becomes north, and this used to be south where the yellow dot is, but now it's north, and this used to be north and now it's south, it's pushed and pulled again. So it keeps rotating in one direction. In this case, keeps going clockwise around and around and around. And this is a direct current motor. The trick to it, which makes it different from alternating current and a generator, is it's got gaps called in the commutator. Gaps mean that at one point it's touching nothing, and if it touches nothing, the armature doesn't have electrical current going through it. So here's a St. Louis motor. Again, the parts to a St. Louis motor: the armature, the thing that spins. So you would hook up a drill bit or something to this spinning part. There's the spinning shaft in the real one. It's got brushes, and there's the split part of the commutator, and it's got permanent magnets. So that's the parts to a St. Louis motor, and that's it.